Greetings, my name is Megh Kanvinde. I am a student studying MSc Applied Geology at the Department of Earth Sciences, IIT Bombay. And today I'll be speaking about carbon sequestration in basalts with a numerical modeling perspective. So let me get to the fundamentals first. What is carbon sequestration, carbon capture and sequestration? It is basically the long-term storage of anthropogenic carbon dioxide sourced from industries or directly from the atmosphere into reservoirs. These reservoirs can be geological or non-geological. Now, geological reservoirs comprise many subtypes such as depleted petroleum sandstone beds, or depleted coal beds, or flood basalt provinces, or even ultramafic rock provinces. But today I'll be focusing mainly on basalts as a mode for carbon sequestration. Now, basalts have numerous unique properties such as their geochemical properties which differ from sandstones and which offer them unique prospects, offer them to be as unique prospects for geological carbon sequestration. So there are quite a few advantages which come with basalt carbon sequestration. One of them is the rapid mineralization and the permanent storage of carbon dioxide. We all know that basalts are filled with minerals which contain cations which can react very rapidly with carbon dioxide. These minerals can react with carbon dioxide and produce new secondary carbonate minerals which can lead to permanent capture of carbon. Now this permanent capture of carbon dioxide reduces or completely stops the risk of leakage in the future, which is not the case in sandstone carbon sequestration. Another very important advantage of basaltic carbon sequestration is the abundance of basalts in the world. Flood basalt provinces are present in almost every continent, and even if we consider our own country, the Deccan traps offer huge potential. Here in the first map you can see all the flood basalt provinces all around the world, especially the ones which are very big. For example, the Deccan traps, the Siberian traps, or the Columbia River flood basalts. In the second map you can see the extent of Deccan basalts, and the volume and aerial extent they provide are very important for future commercial grade carbon sequestration. Now there are a few disadvantages to basaltic carbon sequestration too. Although these disadvantages can be temporary, which can be countered in the long term, but they are still there at the present. One of the main disadvantages with basaltic carbon sequestration are the high costs of basaltic carbon sequestration. Basically what happens is there is no offset to the cost which goes into injection of carbon dioxide into basalts. If you consider enhanced oil recovery or enhanced coal bed methane recovery, the petroleum or methane extracted can be sold to offset the cost which goes into injecting carbon dioxide into the sandstone or the coal beds. But here there is no such product which can be used to offset the costs. Also, the research which has gone into basaltic carbon sequestration and the implementation too is very much in the infancy stages when you compare it to enhanced oil recovery, which is a much older and much more implemented concept. So let me talk a little bit about the general mechanisms which go into carbon sequestration in basalts, which are mostly implemented in the numerical models and the experimental studies. Now, in most numerical models or experimental studies, the injected carbon dioxide is in a separate phase or the supercritical state. Now, the state of carbon dioxide has various advantages to it. One of it is it occupies lower volume than gaseous or aqueous carbon dioxide. It is also very easy to keep carbon dioxide in a supercritical state at such pressure and temperature conditions at around 800 meters depth, which is the optimum depth for carbon sequestration. There is another aspect to it which I will get to later, but here you can see the generalized reactions which take part in the mineral trapping of carbon dioxide. Although these reactions are very simplified, if you take even a single mineral which will react with carbon dioxide, the reaction associated with this mineral will be highly complex and the rate laws also will be very complicated. But here you can see that water plays a very major role in carbon sequestration in basalts. This is because water basically acts as a solvent for the reactions to take in. And this also brings us to the challenge of groundwater contamination. Because groundwater is important for sequestration in basalts too, its contamination has to be considered in the future if we are going to commercial grade carbon sequestration in basalts. Now there are more such challenges which have been found in numerical models and experimental studies. One of these models is the pore space reduction, which occurs after a while of injection. Now, pore space reduction is basically because of growth of new secondary carbonate minerals in the pore spaces. And this basically hinders the transport of carbon dioxide after some time of injection has occurred. Also, another aspect to it is the reaction rims, or the formation of reaction rims on the surfaces of the pores. And this is also because of growth of secondary minerals. Now, these reaction rims may hinder the rate or completely stop the reactions from occurring after a while of injection. So these challenges also should be considered before commercial grade carbon dioxide sequestration is taken place. Now here, this is where numerical modeling is extremely essential, because numerical modeling will tell us about what challenges can occur and what solutions we can use to counter these challenges. So before large scale capital investment is done, numerical modeling has to be done to know what can occur, what can take place in case of any challenges. Also, numerical modeling has very good way to model such challenges, because it can model on micro scale, on hand specimen scale, on outcrop scale, on field scale, which can't be done with lab experiments basically. Now let me talk about some partly experimental and partly commercial Basalt CCS projects which have taken place or which are taking place at the moment. The first one is the Wallula Basalt Pilot Project, which is present in the Columbia River flood basalts in Washington State, USA. This project was basically working for 3 years, from 2013 to 2015, where they injected supercritical carbon dioxide as a separate phase, around 1,000 metric tons of it into the basalts over there. So this was mainly an experimental project where their main aim was to gather as much data for use in future numerical models or future experiments, and to spread this data so that it can be used on other basalt provinces too. Now, the numerical modeling over here focused on various aspects, such as the pre and post hydrological testing for quantification of mineralization which has taken place in the basalt, or even the effect of the changes in the relative permeability, the change in the pore spaces, and the associated change with porosity and permeability. Also, the geomechanical integrity of the basalts was taken into consideration, which is very important. Another very important project is the CarbFix pilot project, which is taking place in Iceland at the moment. Now, this CarbFix pilot project was a bit unique, because instead of injecting supercritical carbon dioxide, it injected aqueous carbon dioxide already dissolved in water. This carbon dioxide was basically sourced directly from the adjacent Helshide geothermal power plant, and along with carbon dioxide, even hydrogen sulfide was injected into the basalt. Now, there are some advantages with the condition of injecting aqueous carbon dioxide into the basalt. One of them is the very rapid mineralization. Since the carbon dioxide does not need to dissolve in the subsurface after injection, mineralization can start immediately. Here in this diagram, actually, you can see the results of a numerical model or a simulation, where in the case of separate phase CO2 injection as supercritical state, you can see that mineralization starts after a while, because dissolution has to happen before mineralization starts. But in the case of CarbFix, where aqueous injection is happening, mineralization can start almost instantly, and the time scales are much shorter. Here, even the numerical modeling focused on long-term CO2 transport through the subsurface. Also, they coupled numerical models with lab or field experiments, where they modeled numerical models, the transport, the relative permeability, along with radioactor tracer tests. So the clubbing of numerical models along with field scale experiments was very revolutionary in this project. Now let me talk a little bit about modeling reactive fluid flow in COMSOL multiphysics with the aspect of basalt carbon sequestration. Now, COMSOL multiphysics is a very popular simulation software. It is a finite element analysis simulation software used widely in physics and engineering applications, where partial differential equations are used to make numerous modules which can react or which can talk to each other basically. And these modules can be coupled to form a multiphysics environment. to know or understand the phenomena which can interact with each other, physics phenomena which can interact with each other. So what I did was I combined or coupled the modules of Darcy's law and transport of diluted species in porous media, and I modeled a 2D branching Y-shaped horizontal fracture in basalt, a fracture zone in basalt actually. Here you can see its scale to be around 5 meters in length and 4 meters in height, with the breadth or the width being around 0.25 meters. The gray region you can see in the Y-shaped fracture is basically the porous matrix in the fracture zone, and this porous matrix has a permeability of 10 raised to minus 16 meters square and the porosity of 0.1 or 10%, which is in line with what you see in normally fractured basalts around the world. There is also an inlet on the left side, which is an open boundary, and there are two outlets on the right, which are also open boundaries. Both the inlet and outlet pressures are 2.5 megapascal. And the closed boundaries here you can see emulate the boundaries of the fracture zone, which are impermeable. Now gravity, the effects of gravity have been enabled in this simulation to understand what gravity will do after injection of carbon dioxide and done at such high pressures. There is another module here, the transport of diluted species in porous media, which looks after the reaction aspect of the simulation basically. Here I have basically considered 3 species, species A, species B and species C. Now species A is the ambient groundwater already present in the fracture zone, and it emulates the pre-existing groundwater in the fracture zone. The species B is what is being injected into the fracture zone from the left and from the inlet, and it emulates the aqueous carbon dioxide which is being injected. Species C is nothing but the simple reaction product between species A and species B, which can be considered as the secondary minerals or the solution reaction product. Now the porous medium module here in transport of diluted species and porous media, they also have the similar properties fixed into them, the porosity, the permeability. The initial values are around 306 Kelvin, the temperature, and pressure is, as I said, the inlet pressure and the outlet pressure, 2.5 megapascal. The reactions are also simple reactions with rate laws fixed, and the inflow and outflow is the same as the inlets and outlets. So let me get to the model results. For species A, we can see the concentrations with time in the fracture zone, and initially you can see that species A has a concentration of 7 moles per meter cube. Here you can see it as red, but after 40 days you can see that species A has moved towards the right, and there is 0 concentration here of species A because of the injection of species B. After 80 days you can see that species A has almost left the fracture zone, and it is only present at the peripheries of the fracture zone. Now let's move on to the concentration for species B with time. Initially you can see, since injection has not happened, species B has a concentration of 0 in the fracture zone, but after 40 days of injection you can see that the initial injection concentration of species B can be seen on the left side of the fracture. This concentration is 1 moles per meter cube. But a very peculiar thing happening here is the exceeding concentration of species B here. It is exceeding the initial concentration or the injection concentration. So it is getting increased to values more than 1 mole per meter cube over here. You can see a small red spot over here. And after 80 days you can see the concentration of species B has almost homogenized across the fracture zone except the outlets. Now species C, which is basically the reaction product, you can see that the initial concentration is of course 0 moles per meter cube because no injection has happened, but after 40 days you can see a reaction front moving. This reaction front basically indicates the boundary between species A and species B. You can also see a very interesting thing that species C has progressed more in the lower branch of the fracture. This is mainly because of the effect of gravity. Here after 80 days you can also see that the reaction front has moved towards the periphery of the fracture, almost exiting the fracture. There is one more thing which can be talked about, is this small point. This might be because of the inlet pressure, and this has been shown in Wu et al. 2021, which also does numerical modeling, and they show that the concentration of carbon dioxide is more in the junctions of the fractures. So this might be related to that too. Now let me get to the conclusions here. So this model was basically a very preliminary model to show how reactive fluids flow through basalt fractures with such high injection pressures and such low permeability and porosity models, which we normally see in fractured basalts. But further work can include reactive fluid flow in entire lava flows, so that we can do field scale modeling basically. And these models can include the entablature or the colonnade, which are very, very potential targets for carbon sequestration in the future. These simulations can also include geomechanical integrity of basalts, which will also be important because the areas which are very, very good for carbon sequestration in the future, they are inhabited by humans. So we have to consider geomechanical risk, geomechanical integrity of these basalts. So that is it. Thank you so much from my side.